Hello everyone, welcome back to another video. This is the second part of the B tree. In the previous part, we have covered what B trees are, how do they work, and how insertion and search operations are performed on a B tree. If you have not seen that video, I would highly recommend you to go and watch that because that sets the base of this video. Okay, let's start the topic of this video, that is deletion from a B tree, or you can deletion in a B tree. Fine. So for all the examples related to this, I am going to take order of tree as 5. The reason I'm choosing 5 is 5 is a perfect blend of not a very large tree and not a very small tree. So with this, you will be able to understand all the complexer scenarios as well. So when we talk about deletion from a binary tree, there are many scenarios possible. So we'll cover all of those moving forward. So let's take an example. Start with an example. So because m is 5, the maximum number of keys that a node can have is 4 because we have seen that formula, right? So let's say this is our root node 40, 60, and 80. Less than 20, we have 5, 10, and 15. Let's assume these three. Between these two, we have 22, 25. Between these two, we can take 45 and 55. Between these two, let's take uh, mm, 70 and 75. Let's take one more example, 79. And above 80, let's take 85 and 95. Okay. So in this video, in this example, all the criteria are being met. The minimum number of keys per node, that condition is satisfied because for a node of order m, the minimum number of keys required are 2. That is satisfied. Okay. Now let's talk about deletion. The first case is pretty straightforward and simple. Deleting from a leaf node. Deleting from a leaf node. In this case also, there are two possibilities. What is the first one? Node has enough keys after deletion, and B, node does not have enough keys after deletion. Okay, so yeah, let's talk about this scenario. If you see in this example, let me copy this example to be easier. Copy this and then paste it here. Okay, yeah. So here, if you see, let's say we try to delete, let's say we try to delete 75. What will the first step is to locate 75. So 75 will lie between 60 and 80. So we will come to this node and we will find 75 here. So we will remove 75. Pretty straightforward, right? So let's clean this graph and we can remove it here only. Let's remove 75. So this is the state of new graph, new tree. Okay. Now if I want to delete any other node from this, what will happen? Let's say I want to delete 79. Okay. So now if you delete 79, you remove it, the tree looks like this. Is this valid? No. Why? Because now this key, it is not meeting the minimum criteria, minimum number of keys criteria. So this is called as underflow. Okay. Now, in that case, what happens? So, in that case, we merge this key with either of the sibling. So, here we have 55 as one sibling, 45 and 55, and another sibling is here, 85 and 95. So, we can merge this with either of these. So, for this example, let's consider merging it with this the left node. So, there's a rule. When you merge any of the node with a sibling node, you take the parent also. So, what is the parent that comes between these two? Let's see. So 45, it lies between 40 and 60, and 70 is greater than 60, between 60 and 80, right? So the parent that is formed here, let's take a color. This is the uh, right. So this is the parent of these two nodes in a way, or this key lies between these two nodes. So in that case, when we merge it, when we are merging it, so what we do is we take the parent and bring it in the node. So 45, 55, 60, and 70. So we bring 60 from the parent, right? So this is how the nodes are formed. Now we see whether this node is it meeting the minimum or the maximum number of nodes keys criteria. It is meeting, so that we are fine with it. So how does the new tree look like? Let's build that now. So we have 20, 40, 60 has been removed. So no 60 anymore. This is in the root node. Less than 20, we have now 5, 10, and 15. Between 20 and 40, we have 22, 25. Between 40 and 80, we have these nodes now. So 45, 55, 60, and 70. And greater than 80, what we had earlier was 85 and 95, and that remains the same. So this is how you deletion, like you delete from a node when it does not have enough number of nodes. I mean, enough number of keys. Let's take one more example to get a better understanding. Okay, I'll take the same scenario again. So let's say now I want to delete 25. Okay, what I'll do is delete 25. So when you delete 25, this is removed, and this is the state of that node with only one key. So let's remove this. Correct? What happens now? Now we have the option to merge 22 with. Oh, before merging, okay, there was one more concept that I actually missed. So let me go back a little. So then before merging, there is a concept of borrowing. What is borrowing? So if we see the left sibling and the right sibling, we see whether we have enough number of nodes to like whether the siblings have enough number of nodes to borrow from. So if we, let's say if we borrow from 15, it will have 5 and 10. That is okay, right? That meets the minimum number of nodes criteria. But if we borrow from 45, that also will have 3 nodes remaining. That also meets the minimum number of node criteria. In the above example, when couldn't have borrowed from this node or this node, because if we had borrowed 55, then 45 would have been alone, right? That makes the tree invalid. And similar to this case, if we borrow 85, that makes the tree invalid. Okay, so this case is in this case we can borrow. So let's see how borrowing works. Borrowing. Okay. So when you borrow a key, what happens is we update the root node, the parent node, because obviously it's obvious, right? So let's say I borrow 15 from here. So how it will look like? So it will look like 5, 10, 15, 22. These look fine. But our parent has 20, 40, and this belongs to this tree, and this belongs to this tree. Do you think this is okay? Between 22 to 40, 15 cannot come, right? So in that case, when you borrow a key, let me erase that again so that I can draw it here. Okay. Now, when you borrow a key, we update the parent. So the parent of this node is 20. So what we do is we move this key to the top and we borrow that from the parent. So let me see. Let me show you what I mean. So let's say we have 5 and 10. We borrowed 50. So it was supposed to be 15 and 22. But what will happen is after borrowing from the left node, we exchange this. Okay. So what it looks like now is, let me put the right side. Yeah. So how it will look now is we will have 15, 40, and 80 in the root node. Less than 15, we have only 5 and 10 because we already borrowed node 15, which made the state look like this. But the tree was not stable, so we exchanged from the parent. Okay, so 15, 40. Now between these two will come 20 and 22. So this will become like this, 20 and 22. This is our new state. Between 40 and 80, again the same cases, I think 45, 55, 60, and 70. And above 80, we have 85 and 95. Let's take the same example and repeat it again. Let's say I want to delete 22 now. Delete 22. When you delete 22, this node becomes unstable again, right? Can you borrow from the left tree? No, you cannot, because left tree already has the minimum number of keys. I mean left node. Can you borrow from the right node? Yes, you can, because it has more than the minimum number of keys. So how will this node look like? This node will look like 20 and 45 after you have borrowed. And this node will look like 55, 60, and 70. This is the updated state of this node. Now, like I said, we have to update the parent also. The parent is 15, 40, and 80. Again, it's the same case. So which node comes between these two? So if you see this, oh, sorry. So here yeah, and remove this. Let me remove this one and draw it again. So between 40 and this, 40 comes, right? We have seen 40 comes here. So we will exchange it from 40. How it will, how that will happen? We'll exchange this two nodes because if you see the condition is not satisfied, how this is 15, yeah. So 5 and 10 here, 5 comma 10 here. Between 15 and 40, what is 45 doing here? That is incorrect, right? So that's why we have to exchange from the parent also. So then our updated nodes looks like 15, 45, and 80. On the left hand side, we have the same node that was existing. This will be updated to 20 and 40 because we exchange this from the parent. This will now become 55, 60, and 70, and 80 is remains whatever it was 85 and 95. 85 and 95. Awesome. So this was the first scenario that we spoke about. That is, node has enough keys after deletion, and node does not have enough keys. So, okay, we have not talking about node has enough keys after deletion. So let's say if you want to delete from a leaf node, let's say you want to delete 70, you can simply delete 70, right? No issues. Everything remains fine. There is no change. You don't have to borrow. You don't have to, uh, merge with any other node. That's all you get. 70 is gone, just like that. But now if you have to delete again, you will have to do the merge operation. I'll quickly repeat the first example that we took. So let's say in this case, I want to delete 60 now. Delete 60. You delete 60. You cannot borrow from the left node. You cannot borrow from the right node. The only operation uh, you can do is you have to merge it from either of the nodes, either on the left side or on the right side. Let's say I decide to merge it on the left side. So it will become 20, 40, and 55. But when you merge, you have to take one key from the parent also, right? So what happens? So which parent key lies between these two? So this is this, right? So 45 lies between these two. So we will bring in 45 here. That will make it 40, comma, let me draw it again. So 20, 40, 45, and 55. This is our new node. Okay. And this also has the maximum number of nodes. I mean, no condition is being broken here. Okay. So how will it look like now? So our root will look like this. It is now 15 and 80, only two nodes, two keys in the root now. Left hand side of this would be 5 comma 10. Middle, we just merge the 20, 40, 55, sorry, 45 and 55. And greater than 80, we have untouched 85 and 95. No rule being broken, right? This was the condition when we have to delete from the leaf node. So these were all the scenarios. Now, let's say now we have to delete from from any internal node. What are internal nodes? Let's see that. The second is deleting from an internal node. Okay, let's see the same example back. So if I try to copy the example that we took earlier, hmm, yeah, this is good enough. Copy this. Okay, let me take a new example altogether. So what we can do is, let's say we have a node 50 from 100. The left node of this has 20, 35. The middle node of this has 60 and 75. The right side has 110 and 125. Okay. Now this has 10 comma 15. Middle we have 22 comma 28. On the right side we can say we have 38 comma 40. Okay. Now similar to this, we can say we have 55 comma 58. Between this we have 65 comma 68. Above this we have 78 comma 80. Okay. We can leave it the right side as it is, as that is not required. But we cannot do that. The reason is all the leaf nodes are at the same level, right? That is how the tree gets restructured when you are inserting the nodes. So it ensures that property is maintained. So let me add that in this uh, diagram only. I can skip it in the future diagrams 130 and 135. Fine. In this case, this is an internal node. Sorry, this right here is an internal node. This is an internal node. This is an internal node. Now, if you're planning to delete a number from any of these nodes, in that case, what happens? So let's say I want to delete 75. Okay. Now, when you delete 75 from here, what happens? The last node of the last key of the node that comes before this is known as predecessor. So this will be the predecessor. But the rightmost, no, I mean not the rightmost, but the right next key. So after 75, this is called as the successor. To repeat again, this is the node. It has two keys, 60 and 75, right? And it has three children. This is one, this is two, and this is three. Now, when we talk about 75, because we are removing the 75, the two children which are attached or in direct relation with this is this node, node this one, and node this one, right? The predecessor is the last element of the node which comes before it, and successor is the first element or the first key of the node which comes right after it. So this is called as predecessor and this is called as successor. Okay, I hope that is clear. Now, when we are deleting the key 75, we have to exchange 75 with one of these keys. What do I mean by exchange? Let's see that. So I'll keep it here. I hope this is visible. Yeah. Now, let's redraw the tree quickly. So this is 50, 100. Then we have 20 and 35. Here we have 60 and 75. And here we have 110 and 125. Okay. Now this side we have 102, 105. Here we have 112, 115, and this is 130, 135. Okay. Finally, on this side, we have 55 and 58. This is 65 and 68. And here we have 78 and 80. Let's assume that it is there because we anyways don't need that for the moment. Now, when we are trying to swap these two keys, it will look like this. So let's erase it quickly. So this, I said we have to swap, right? So when I say swap, we were removing which key? 75, I guess, right? Deleting 75. And let's assume we are swapping it with the successor, the predecessor, because this is the predecessor. Now this becomes 68 and this becomes 75. Now we already know how this deletion goes, right? Because we have seen this in our above example. So we can simply remove 75 and when we do that, when we remove 75, this key becomes alone. So we can see if it can be borrowed. What are the two children, two siblings? This is one sibling and this is another sibling. Can we borrow it from there? No, because both of them already have the minimum number of keys. So we cannot borrow it from there. So what we will do, we will merge it. Now again, this is an interesting case actually. So now if you see, when we try to merge this, what will happen? Just to show what we are merging this. I'm merging 65 with the left subtree. What happens in that case? So the new node, it becomes 55, 58, 60, and 65, correct? Now who will be the parent of this? We have already taken out 60 from here. What's left? Only 68 is left, correct? And on 68 left hand side, we will have this. On right hand side, we will have 78 and 80, correct? Now it will have the parent, whatever it is. This one will be the parent, 50 and 100. And the parent will have other nodes. Now, this one is alone. I'm in single node and it is not meeting our criteria. In that case, what happens? We again merge it from one of the siblings. Okay, so just to be clear, let's redraw the diagram quickly. So we have 50, 100. On the left hand side, we have 20, 35. Here we are only left with what? 68 now because that other one is removed. And lastly, we have 110 and 125 with it having three childrens, it having three childrens, it having two childrens. Okay. What are the two childrens? Let's note it down for these at least. So what are the two children that it has? It has 55, 58, 60, 65. And on the right side, we have 78 and 80. Okay. Great. Now, what we want to do, we want 68 is alone. Can we borrow? So, and these are the siblings for 68. Can we borrow? Again, the answer is no. So, what we will have to do, we will have to merge them again. What happens when we merge? So, we have to borrow from the parent node. And in this, the parent node is the root itself. And which of the parent key comes between these two? 50. So, this is how it looks like when we borrow. So, what will be the elements? It will be 20, 35, 50, and 68. And the root will become, let's remove that, and the root will become 100. Left tree and right tree, 110, 125. What happens to the children now? That is the question, big question. So greater than 68, we know it's these two only. So we can do that. We can simply add those 78 and 80. It will have the three children. So this is separated. Yeah. So let's say greater than 68, we are clear. No issues there. Now, when we have merged it, our updated node will have, I mean, the keys that we have to sort are bigger. The content of those keys are bigger. So what were the children of these 20 and 35? Let's see that. It has become a mess, I can see. So the children that we have here are these three, correct? These three. So let's try to create those. So we have 10, 15, 22, 28, 38, and 40. These are the children. Now let's copy this because we have to append. Uh, so these are the nodes that were present that are present only in the 20 and 35. This node basically. Now we have merged two other nodes as well in it. So what are the children that were there in this node? 20, 35, 68. Yeah. So 55, 58, 60, and 65. So we will have to add those also here. What we will have to add? 55, 58, 60, 65. Let's take a pen. 55, 58, 60 and 65, right? 50 and 68, I'm sorry. Yeah, 50 and 68. Wait, 60 and 65. Yeah, I was seeing it wrong. So it's 55, 58, 60 and 65. 55, 58, 60 and 65. Now we will have to combine these nodes and reassign them wherever they come in this tree. So what do I mean by that is, so we have these nodes to assign here, right? Let's see what all nodes come are there which are less than 20. Okay, easy task for us to figure that out. So we have what 10 and 15, correct? What are the nodes between 20 and 35? So we have 22, 28. That's all, I guess. Between 35 and 50, we have 38, 40. Those two. Between 50 and 68, we have 55, 58, 60, and 65. And less than 68, we already have. So this is how our new tree will look like. Now let's suppose there was a scenario in which 28 was not there. 22 would have been alone, right? So in that case, again, the same process that we have seen till now. Either we will see first whether we can borrow from the left or right. We cannot. We will merge with either the left one or the right one, and the new tree will be updated. So this process keeps on happening recursively, and this is how our trees form whenever any operation, delete operation or add operation is made. So this was B trees. Where they are used. So if you see, mainly like I have already mentioned, it is mainly used in database management and file systems because they enable efficient storage and retrieval. So it makes the process pretty fast. I think we have covered all the cases. Let's quickly go back up and see. We have covered quite a few things. So we saw deleting from a leaf node. We saw deleting from an internal node. In the leaf node also, there were a couple of scenarios like the last node, the last key, when the minimum number of keys are more. All those scenarios we have already covered, correct? Uh, I think this is it. So let's say if you want to remove from the root node also, in that case also the same process will be followed. So we will see the predecessor and the successor will swap between these two, and then we will remove it. Let's say this became 100, and this became 68. 68 became the new root. 100 can be removed simply, right? And yeah, so this is no longer there. What happens to this child? So we will merge these two and then reassign, because this will obviously overflow, right? When we merge these two, and another parent will be formed. The same process that we have seen so far. I think that's it for this video. Thanks a lot for watching. I hope you learned something new. If you have any request, or if you want me to cover any other topic or need any clarification, please do comment. I will try to clarify. Thank you.